students, my name is Pallavi and welcome to our channel Parallax Tutorial. Today we are going to discuss the last 4 questions of the paper which we were already doing, and the paper number is 062504. This is a physics theory extended paper. This is the specimen paper for the year 2023, and we have already done the question up till question number 8. Please look into the comments for the previous videos where we have already solved these questions. Today, we are going to start with question number 9. Now, as you can see, it will be question number 9, 10, 11, and 12. That's what we will be doing in today's video. Let's have a look at this question. Please remember, the rules are still the same. That is, I will be using a red ink just to explain the concept whenever required. However, I will be using blue ink on the paper so that you know what to write in the answer column, right, over here. So I'll be using blue for that. Red will be used only for explaining the theory if you need to know that, or for further detail, right, in further detail. Okay. So the question number 9 says, figure 9.1 shows a conducting ball that oscillates between 2 charged plates. So these are the 2 charged plates. As the ball oscillates, it touches each plate in turn. Referring to the charge on the ball, explain why the ball moves to the positive plate after touching the negative plate. Let's have a look at the answer. The number of points this answer holds, it's 2. Therefore, 2 solid points required. So what do? The question says you have to refer to the charge of the ball after it has touched the negative plate. Now, as you see, when the ball touches the negative plate, it will acquire a negative charge, right? And it will be attracted towards the positive plate. Therefore, it moves towards the positive plate because unlike charges are attracted towards each other. This is exactly what you have to write. So the first point which you will write is ball gets a negative charge after touching the negative plate, right? It has acquired a negative charge. That carries 1 mark. Then the second point would be, since opposite charges attract each other, the ball therefore starts moving towards the positive plate. Okay, that will carry the next mark. This was pretty simple. Let's move on to the next. State which particles move when there is a current and state the direction in which they move through the sensitive ammeter. This is the sensitive ammeter. Now, this is an easy but sometimes a tricky question, you may call it. They have asked which particles move when there is a current. So the particles which are responsible for flow of current is flow of electrons, right? We always know that current is basically flow of electrons. Electric current is flow of electrons. So the particles which you will name is electrons. Now here comes the trick. You have to specify the direction through the sensitive ammeter. It will be the direction of electrons. They have not asked what is the direction of electric current. Remember, conventional electric current, let me write it over here. Although you don't need to write this in your exam books. So conventional electric current, the direction of conventional electric current rather, you can make a note of this in your notebooks. Direction of conventional electric current is opposite to that of electrons. Which means if you have to specify the direction of particles in this particular question, it will be electrons which will be repelled from the negative terminal of this voltage supply. Therefore, they will be flowing from left to right through the sensitive ammeter. And that will be your answer, left to right through the sensitive ammeter. I have just written it in just the keywords. You can just make it 1 sentence for the answer. And this carries 2 marks. So as I said, it's an easy but maybe a tricky question. Now moving on to the last part of this question. For each complete oscillation of the ball moving between plates, a charge of 8.5 into 10 to the power minus 10 coulombs. So let's write down the charge. Charge is 8.5 times 10 to the power minus 10 coulombs is transferred from one plate to another. The frequency of oscillation, so the frequency is given. Remember, frequency is 1 by T. Okay. and it is equal to 4 hertz. Okay, that means T would be 1 by 4. You have to find the current. Current, if you know the definition of current, it is rate of flow of charge or electric charge, okay, which is Q by T. So you have Q, which is 8.5 into 10 to the power minus 10 coulombs. And you divide it with T, which is 1 by 4, plug it into your calculators, and this will be the answer which you get. This carries 3 marks. You have to show the working over here, okay? And this is how you calculate. I hope this was clear. Moving on to the question number 10. An americium nucleus decays by the emission of alpha particle into neptunium nucleus. The symbol is already given to you. Now it is a decay of alpha particles, so you have to complete the nuclear equation for this decay. Now how do we do that? So for any nuclear equation, please remember whatever you have on one side, this is the mass number, this is the atomic number. Okay, again, concept. You may take down notes if you feel so. When this parent, this is called the parent nucleus. When this parent nucleus decays, it gives way to a daughter nucleus and the corresponding particle which it decays into or it emits. So doesn't decay into it. You won't say decay into, you'll say it emits a particle while it decays. So it decays into the daughter nucleus, but it emits an alpha particle in this case. Alpha particle's mass number is 4, atomic number is 2, which means your daughter nucleus will be A minus 4 and Z minus 2. Now, why did I write this? Remember that now this is the main essence of all these reaction-related questions. So you look into the two sides of the equation, the left-hand side and the right-hand side, and you match the mass numbers on both sides. So you have A over here, so the opposite side, that is the right-hand side, should also have the total mass number as A. So A minus 4 plus 4 is actually A. Therefore, the daughter nucleus Y will have A minus 4 as the mass number. Similarly, you also match the atomic number. So if it is Z on the left-hand side and Z minus 2 on the right-hand side, Z minus 2 plus 2, because there's an alpha particle which is emitted, so which is also Z. So the atomic number has to be equal on both sides of the equation. Similarly, mass number has to be equal on both sides of the equation. Therefore, this is how you make an equation. Now, applying this rule into this, let's try to solve this. I have deliberately kept it empty so that I can solve it in the video, right? So we have 241 as the mass number of americium and 95 as the atomic number. So it gives neptunium, which means an alpha particle, right? Two things are given. So alpha particle, we'll write down that one first. 4 and not A, 4 and 2, obviously. And then what will happen to the Neptunian? It will become 93 because 93 and 2 add up to 95, which matches with the atomic number. And Neptunian's mass number would be 237 because 237 and 4 add up to 241. So the mass numbers are also equal. Now let's talk about the second part. Americium is used as in smoke detectors. Explain why beta emitters or gamma emitters are not used in smoke detectors. It's just a one marker question. So there is only one explanation for this. Alpha particles, they are very ionizing, they're highly ionizing as compared to beta and gamma. So therefore, some mechanism must happen. Therefore, they will ionize the smoke particles, or due to which they will be able to detect the smoke particles. You don't need to go into the details of what exactly happens because it's just a one marker. Therefore, the main point which will carry that one mark or which will give you that one mark is just writing down that alpha particles has more ionizing power than beta and gamma. So beta and gamma emitters will not produce enough ions, due to which in smoke detectors, you use only alpha particles. Let's come to the B part of this. The half-life of americium nuclide is given as 470 years. A sample of this nuclide contains these many atoms. After some time, these many americium atoms have decayed. That means these many americium atoms have already gone. So how many are we left with? We are left with 8 into 10 to the power 14 minus 6 into 10 to the power 14, which is 2 into 10 to the power 14 atoms are left now in this americium nuclide, right? Now, it says that you have to tell the time required for this decay. Now, how do we do this? For this, let's very quickly understand the half-life concept a bit so that you can do similar questions if they come. So remember, the half-life curve is something of this sort, okay? It's like an exponentially decaying curve. It never reaches the x-axis, which is the time in this case. It's an asymptote. And this is the activity. You may call it activity. You may call it how much nuclide is left, as in this case, right? So suppose the half-life in this case is 470 years, let's say. What do we mean by this 470 years? It means that if presently, then let's say this is the nuclide, the value, okay? When time is 0, presently, let's say this is, in this case it is, how much is it? 8 into 10 to the power 14, right? It will take, now when we say half-life is 470 years, it means from 8 into 10 to the power 14 to become half of it, which is 4 into 10 to the power 14, it will take 470 years. I hope this concept got clearer. Now, again, now it is 4 into 10 to the power 14. So to decay again to half of its value, which is 2 into 10 to the power 14, it will take another 470 years. So there we go. Now the sample is left with 2 into 10 to the power 14 atoms. That means the total number of years will be 470 into 2, which is 940 years. That will be the time required for the decay to happen. That is 6 into 10 to the power 14 americium atoms have already decayed, and we are just left with 2 into 10 to the power 14 atoms. Now, if you can keep on going and calculating the half-life, the number of atoms will always reduce to half of their original value, but they will never touch the 0 mark, or they will never go, right? There will be always a radioactive substance there in the universe once it has been radioactive. I hope I made some sense there. Okay, let's move on to the next question. So question number 11. Now, this is a very, very theoretical question. So I would like to explain a bit on this, but I would suggest please read through the notes of how a stable star is formed. And this question, I have seen this question quite often coming in the exam. So let's move on. Describe and explain how a stable star is formed. So this basically starts from, let's begin from the beginning, right? Now, these are the 3 points which will give you the 3 marks, okay? But I will be explaining a bit of this so that you understand the concept as well. Starting with nebula. So how does a stable star form? So it's basically there's a supernova explosion, okay? And all the dust and gases, they started coming together. They start coming together. So hydrogen and dust, when they start coming together under the force of gravity, imagine huge, massive, mass of hydrogen gas and dust coming together. They will be pulled together, right? And they will try to take a shape, a rough shape, spherical, maybe. But that's what is nebula. So nebula is formed when all the dust and the gas, they come together and they are pulled inwards by the process of gravity. Remember, it's not stable yet because the only existing force is the inward pull. That is, everything is coming together due to gravity. Its mass, it's very massive, so they are coming together due to gravity. That's the only force which is existing right now. That's nebula. Let's move on to the next stage, which is protostar. Now, what happens in this stage? So when these particles are coming together, obviously they are colliding with each other. So the temperature of these hydrogen particles, it starts increasing. So there is an increase in temperature. So the temperature of this nebula starts increasing, and this is where it is called a protostar. Okay. Still, it is unstable because, again, the reason is still the same. That is, the force existing is the force of gravity. Now comes the third part. So now when they come close enough, nuclear fusion between the hydrogen atoms start happening, right? When nuclear fusion starts happening, what happens? We have learned about nuclear fusion, right? Two small nuclei, they collide and they give or fuse together to form a bigger nucleus, which is a helium nucleus if two hydrogen collide to form helium. And when this happens, remember, it is happening in the centermost point of the star or core of the star. Okay, that's where it begins. So all the smaller nuclei, they are coming together, they're fusing, nuclear fusion happening. And as a result, immense amount of energy is released. Or there is a force which is called outward pressure force. And this force, so you may like to note this down. This is the outward pressure force, which will be the force which from existing from the core of the star, and it is going outward. Okay, this is due to the nuclear fusion happening. Now, when the blue becomes equal to the red, that's when a stable star is formed. In other words, when the outward pressure force balances the force of gravity, which was the inward pull. See, they are still pulling, right? Because it's very massive, so it's getting pulled towards the center. All the dust and the gas which you have, which is there in the star, is getting pulled towards the center. So that inward force of gravity, when it equals the outward pressure forces, then there is an equilibrium, or the star is called a stable star. Our sun is currently in that phase. So this is how a stable star is formed. In your exam, it's the 3-marker. You need to put 3 solid points, explain nebula, explain protostar, and explain what happens, or what are the two forces basically which balance each other and therefore lead to a stable star being formed. So these will carry 3 marks. Moving on to the next and a very technical question, I would say, because it's very theoretical, but I have seen students struggling with this particular question quite often. So let's see what exactly this cosmic microwave background radiation is and how it helps us prove that universe has expanded. So first I will go according to what you need to write in the paper so that you know what exactly are the keywords and how many marks they carry, etc., etc. Then I will just explain a bit of how this cosmic microwave background radiation, what it really means. Okay, so let's go through the points first. See, microwave radiation is observed at all points in space around the Earth. So basically, we are talking. So the question is, describe and explain what can be deduced from the cosmic microwave background radiation. That's the question. What do you deduce from the background radiation, which is cosmic microwave radiation in the cosmic microwave region? What do you deduce from that? That's what we have to describe. What does it basically mean? That's what they have asked. So the first point which you will say is microwave radiation is observed at all points around the Earth. Okay. This radiation was produced when universe was formed. I'll come to this point. Then it says the radiation has expanded into the microwave region of the electromagnetic spectrum. And this is the evidence that the universe has expanded. Now let me explain this a little bit. See, when we talk about cosmic microwave radiation in particular, okay, we are talking about, over here we are talking about how the universe came into existence, right? I will show you a picture of the cosmic microwave background radiation. Let me see if you, yeah, have a look at this. I hope this is visible. Right? Okay. So, keep looking at the picture and let me explain what exactly this is. Right? So, we talk about Big Bang theory. Now, cosmic microwave background radiation, let's talk about the property of it. It is a remnant from early stages of universe. Okay. We are going to prove it anyways. The wavelength currently, which is measured, is in the region of the microwave. Therefore, it's around 1 millimeter. Therefore, it is called cosmic microwave background radiation. Now, it is observed that this radiation exists in the electromagnetic spectrum region of microwave region of electromagnetic spectrum, and it's coming from all direction, and it is generally at around 2.73 Kelvin. Okay, that's the temperature. Now, according to Big Bang theory, the early universe was very hot and very dense, right? So, because it was very hot, it must have emitted thermal radiation. Okay, and currently the radiation is in the region of microwave region, right? However, 14 billion years ago, the radiation must have been in the high energy region or in the gamma end of the spectrum, like you see in the picture over here. However, over the period of 14 billion years, there has been a red shift which has happened. And over the time, due to this red shift, the wavelength has increased, and therefore it is now in the microwave region of the spectrum. I hope this made some sense. The cosmic microwave background radiation is also very uniform. So that's the reason why the profile of this cosmic microwave background radiation exactly imitates that of a very hot body that has been cooled over a period of time. So now have a look at this diagram. So this is what I wanted to speak about cosmic microwave background radiation. So when the universe, when the Big Bang happened, the radiation must have been like this: very high energy, high frequency, low wavelength. Over the period of 14 billion years, the wavelength has increased, and now it is in the microwave background radiation, microwave region. This is called redshift. So I hope I have explained a bit of redshift also to you all, and I hope this was clear. Now, we are going to move towards the last part of the paper, which is the next question. It is on a transformer. I hope this is visible. Right. So this is the diagram of a transformer. Yes, I will explain a bit of what the transformer actually does, and then you can do the question, or we'll do the question first and then I explain what a transformer is. For those of you who already know the transformer, they can just see the work, right? So the question says there are 8,000 turns in the primary coil of the transformer. The primary coil is connected to a 240 volts mains supply, which is over here. This is the primary coil, okay? And a 6-volt lamp connected to the secondary coil operates at full brightness. You have to calculate the number of turns in the secondary coil. So you use the formula Ns by Np is equal to Vs by Vp. Okay, so Ns, the number of turns in the secondary coil, that's what you're calculating. Ns by Np, which is 8,000, will be equal to Vs, the voltage of the lamp in the secondary coil is 6, divided by the Vp, which is 240, and then you solve and you get 200 as the answer over here. Next, the current in the lamp is 2 amperes. The transformer operates at 100% efficiency. What do we mean by it? That whatever is the power input, that is the power output. You can also say energy input is equal to energy output. Whatever you give in, you get back. Full, 100% of it. That's what it means by 100%. Power means VI. That's the formula for power, voltage into current. And so primary, I primary will be equal to V secondary, I secondary. Current in the lamp is 2 amperes, which means secondary current is 2. Vs, do we know Vs? Yeah, we know it is 6. And that is the lamp's voltage. Do we know Vp? Yes, we know it is 240 volts. And we need to find the current in the primary circuit, which is Ip. So you just divide 12 by 240. That's your Ip in amperes, which comes out to be 0.050 amperes. Now, this was the question. Let's very quickly understand what a transformer is and how it works, right? So why do we need a transformer? Think about it. Let me give you some time to think about it. Why do you think we need a transformer? Think. What do they do? Okay. 1, 2, 3. Yeah, let's go. So transformers are basically, let's say you have a power station over here and your house is very, very far away over here. Okay. Now the power station is giving a certain voltage. You put a transformer next to the power station, which is a step up transformer, which ups the voltage. That is, it increases the voltage. And it is carried through high voltage lines through long distances. So this is done mainly to mitigate any power loss or minimize power losses. Again, just before your house, again, there is another transformer, which is a step down transformer. And that again brings down the voltage and it goes to your house. So this is basically done to make sure that there is no power loss. If you supply the voltage from the power station straight to your house, there may be a lot of power loss and therefore a lot of energy lost. Therefore, we use 2 transformers in this process. Therefore, you receive exactly the amount of voltage which you want and with minimum difficulty. Okay, now let's see how or what is the mechanism of this transformer. So clearly, as you see over here, this is a step down transformer. Now, why do I say that? Look at the number of turns or number of turns in the coil. Yeah, this is the primary coil. It has more number of turns as compared to the secondary coil. So what exactly happens? So transformer basically is based on the mechanism of electromagnetic induction. Let's see how that helps over here. So electromagnetic induction is basically electricity induced due to magnetism and vice versa. Okay. So vice versa is also there. Magnetism induced due to electricity. Let's see how that works. So you have an AC input over here. So electricity you are providing. This electricity goes to this primary coil, right? It passes through the primary coil. Now we know that whenever there is electricity passing through the coil or through a wire, there is a magnetic field around it, correct? There is a magnetic field around it. Now this is a coil which is in the form of a solenoid. So the magnetic field or the lines of magnetic force will be through it like this, right? Through the coil. So the magnetic lines of force will pass through this, correct? That is how it will pass. Let me make it a bit better. So we have magnetism induced due to electricity in the primary coil, right? These are the magnetic lines of force. Now, the rectangle which you see over here is basically a soft iron core. Its job is mainly to keep the magnetic field lines inside it and not outside, right? Okay. So this is what it does. Okay. So all the magnetic field lines are now passing through the secondary coil, which is this. But nothing will happen over here because electricity will be induced only when there is a changing magnetic field, correct? So from where do we get a changing magnetic field? If you have an AC input, remember AC input means the current or the voltage which you're giving is continuously changing. Therefore, the magnetic field lines are also continuously changing. Lower, more, like that. Therefore, you have a changing magnetic field in the secondary coil. This is the secondary coil. If there is a change in magnetic field, changing magnetic field around the secondary coil, then electricity gets induced in the secondary coil, and therefore that electricity is flowing through this lamp. This is how a transformer works. I hope this was clear, and I hope you understood the whole paper. With that, we come to the end of this series, this paper series. I think there are around 4 videos. Please go through the rest of the videos. I hope you liked this video. If you did, please don't forget to subscribe and like. Thank you so much.